Hello, my name is Karlo Jukic, and this is Lab 2. Introduction of this lab is that the purpose is to create a better simulation on GlowScript to model a distributed charge across two pieces of tape and how they interact by modeling them as line charges rather than point charges from the last lab. The overall results is that this model was successful in more accurately modeling charges, and the Q came out to be 2.680 e to negative 8 coulombs. Fundamental principles of this lab are largely the same, with F equals ma being Newton's second law and Coulomb's law describing the force resulting from the presence of multiple charges. In this lab, we also have the electric field distribute charges, which is the sum of all fields of a particle to give the total E net field that we're going to be using for this lab. System setup and analysis largely the same also. System being tape B, the surroundings being tape A. Our assumptions are there's no air resistance, the tapes are neutral until charged, and the charge was evenly distributed across the tapes, and the initial conditions are the same. Here's our analysis from lab 1. If you want to go over it, I'm going to skip it. Here's our GlowScript code, where we have defined our physical constants up here, and we add our observed values from lab 1. And here we have our estimated charge, which we're going to play around with this new constant until we get a good number in our model, but that comes later. Here we'll define a function for electric field, just going back to Coulomb's law. Charge a particle, get our E field, which is just our k constant times charge over the magnitude of r, which is our direction vector times the direction. Get our E field, which is just force of E field from Coulomb's law divided by a secondary charge. And then we'll define a line of charge. This is what the main part of the lab is going to be. Instead of defining it as a single point charge for each of the tapes, we're going to create a line of charges of a certain amount and then calculate how each charge will affect each other and how it will affect the overall E field. And just down here, we have our definitions of tapes, with the top tape having the total distance over 2, which is just the separation distance, and negative separation over 2. Continuing on the code, we're going to start defining start calculating our E field, our total E field, and our forces due to the field and gravity. Basic gist of it, we're going to start calculating our total E field with respect to all of the different particles combined. We'll turn those into force vectors as well as the gravity vector, which we'll just use F equals ma. And down here, we'll actually get our vectors as arrows. And so we'll have our FE arrow, which is just our FE scale, which is our just calculated net field times the FE on the top, which is the force on the top tape. And then our FG arrow, which is just -1 times mg, -1 as a down direction, times our FG scale. And then we'll go ahead and print both our values. For our results, here's what our model looks like. And we got a pretty close value with playing around with that constant of a force of 2.11 83 e to -3 newtons, and is almost the same for the gravitational force. So that gives our charge value as 2.680 e to -8 when that constant from before is calculated out. Some sources of error could have been that the tapes could have had different charges when we were actually calculating this out, and that other forces were acting on the tape, such as air resistance. Some similarities that both models don't really show how much the tape would curve or any other interactions tape would have geometrically. It's a similarity, and the difference is that there is a 201% difference between the two Q values given in either labs. So our discussion: what if you had modeled each of your tapes as a single point charge, like in the previous lab? And comparing these values, we see, as I said before, that's a 200% difference on the Coulomb value. And these estimates matter on the Y question because these are a differing level of precision calculations, and more often than not, having more precision will give you a more accurate answer. So calculating this tape as a line charge instead of just a singular point charge generalization will give us a value that's closer to what should actually be true. The conclusions for this lab is that modeling anything with more precision is bound to give more accurate results, which was the case for this lab. And this lab could also be expanded on further by going into more precision on how the tapes interact with each other with different forces and differing geometries. Thank you for watching.